Reciprocal identities. We've actually already done these. Sine of x, that's the same thing as 1 over cosecant of x. Cosine of x is the exact same thing as 1 over secant of x. Tangent of x is the same thing as 1 over cotangent of x. Now we're going to go the other way with it. Okay, your quotient identities, tangent of x. In order to find tangent, it's y divided by x, or sine divided by cosine. Cotangent of x would just be flipped. It's cosine of x divided by sine of x. Please don't worry too much about this. That's stuff that we will explain in greater detail once we actually start working some problems on this particular unit. All right, we have some Pythagorean identities that we are going to need to memorize. The first one is sine squared of x plus cosine squared of x is equal to 1. And then secant squared of x minus tangent squared of x is equal to 1. Then cosecant squared of x minus cotangent squared of x is equal to 1. Reminder, these are things that you're going to want to memorize. Okay, for 1 through 4, what we're pretty much doing is we're trying to solve a puzzle, essentially. So what they want us to do is they want us to get it down, simplify these to a single trig function. Now, what I'm going to do is I'm going to copy down our very first Pythagorean identity that we just wrote down a second ago. I'm going to copy that down here, and then I think that'll better help explain what we're trying to do. Okay, so there's the very first Pythagorean identity that we have. What I'm going to do is I'm going to maneuver this equation so that it matches this right here. So I would need to subtract cosine squared of x from both sides. And that would leave me with those cancel. 1 minus cosine squared of x. Now this matches that, doesn't it? And what does this equal? This equals sine squared of x. This is our answer. We have now reduced it to a single trig function. Okay, looking at example 2, notice that we have cosecant squared. So you would want to try and identify which identity is that on the very first page of those notes we took. We see that cosecant, that is identity 3. Identity 3 has cosecant in it, cosecant squared of x. So that's the one that we would want to try and maneuver a little bit and narrow it down to a single trig function. Okay, it looks like what I would need to do is add cotangent squared of x over here. And then we could subtract 1 from both sides. Cosecant squared of x minus 1. cosecant squared of x minus 1. And what does that equal? Cotangent squared of x. This is your answer. Okay, number 3, cosecant over sine, or more accurately, cosecant of theta over sine of theta. So what I want to do is I want to try and have the same function here, the same trig function. We can write cosecant a different way. I'm going to turn my paper over. Cosecant of x is the same thing as 1 over sine of x. So I'm going to change it to that. So instead of cosecant of theta, I'm going to write cosecant of x. It doesn't really matter whether or not you use x or theta. So I'm going to transfer that to, because remember, this is the same thing as 1 over sine. So instead of cosecant of theta, I'm going to do 1 over sine of x over sine of x. So instead of cosecant of x, I did 1 over sine of x because it's the same thing, over sine of x. And then do you remember what this really is? 1 over sine of x over, or divided by, sine of x. Now we're going to do keep, change, flip. Keep 1 over sine of x, change from division multiplication, and flip sine of x over 1 to 1 over sine of x. And now we're going to multiply. 1 times 1, I'm going to write my answer down over here, is 1. Sine of x times sine of x is sine squared of x. Now, doesn't this look like one of those Pythagorean identities a little bit? Let me flip my paper over. 1 over sine squared of x, or 1 over sine of x. 1 over sine of x, 1 over sine squared of x, same thing. And essentially, it doesn't really matter. That is equal to cosecant of x. So we can narrow this down to cosecant squared of x. And now we have our single trig function. Sine squared of theta over tangent squared of theta. I would want to rearrange tangent to where it has sine in it. There's another way of writing tangent, and that would be, in this case, sine squared of theta over cosine squared of theta. So that's what I'm going to change this to here. I'm going to start with sine squared of x over, instead of tangent squared of x, I'm going to do this right here. And this can all be rewritten sine squared of x over, or divided by, and now keep, change, flip. And now we can cross cancel, leaving us with cosine squared of x, our single trig function. That's how you would do 1 through 4. All right, they have given you just some reminders of how you would factor various ways, which I will not explain in great detail here because we've been factoring for a while now. We're going to be factoring today. We're going to be factoring a lot this unit, except now we're going to be factoring trig functions, and it sounds a little bit more difficult than it actually is. If you're pretty good at factoring, this is going to be pretty simple. If factoring has always been an issue for you, you need to let me know that so that we can work on that together. so that I can add some supplemental materials for you to work on, because you're going to have to factor, and you're going to have to factor well in order to be successful in this unit. Okay, so let's look down at example 5. Okay, example 5, sine squared of x minus 5 sine of x minus 24. The way that we used to see that was like this: x squared minus 5x minus 24. This and this will, in a way, help us get to the correct answer. So we would need our factors of negative 24. Subtract to get 5. That's 3 and 8. In this situation, your 3 would be positive, your 8 would be negative. Since we have no number in front of x squared, we can go ahead and plug our factors right into parentheses. So x plus 3, x minus 8. And we're mostly done. The only thing that we have to do is just write the word sine in front of the x. And that would be your answer for 5. Okay, example 6. Here's how we used to see this type of problem. We would now need to multiply 7 times negative 4. We need the factors of negative 28 and subtract to get 3. 4 and 7. In this scenario, 7 is negative, 4 is positive. Now we do have a number in front of our x squared. So we're going to have to create a factor by grouping problem. Out of that group there, we could factor out an x, leaving us with 7x plus 4. Out of that group there, we could factor out a negative 1. Leaving us with 7x plus 4 again. Pretty much done. All the hard work is done. We just now need to write the word sine in front of our x's. Take a look here. Look how you need to write it if you have a 7 in front of your x. Sine is going to be sandwiched between the 7 and the x. Okay, example 7. 9x squared minus x. Actually, hang on just a second. I'm now reading it instead of just mindlessly going through it. Give me a moment to erase this. Okay, sorry for that. Make sure and erase your work or cross it out. Like I said, I wasn't really looking at the problem. I was just kind of mindlessly going through it. And as I was beginning to work on the problem, I realized, oh my goodness, we have sine and we have cosine here. So the way that we used to see this in algebra 2 would be 9x squared x, that symbolizes sine, minus, instead of cosine, maybe we would see y squared. When we have different trig functions and we're trying to factor, you can use different letters. Now what we have here is we have a difference of perfect squares. Difference of perfect squares, different signs. We're going to take the square root of this value here, which would be 3x. We're going to write that there and there. Take the square root of that. And now we just need to rewrite our answer using sine and cosine. Oops, sorry. There's your answer for 7. Okay, looking at example 8. Rather than rewriting this in a format that we're normally seeing in Algebra 2, I'm just going to start by factoring things out that we have in common. So we have a term here for tangent squared of x, and we have another term here, minus 12 tangent of x. So it looks like they both have a 4 in common that we could factor out. And they have tangent in common that we can factor out, tangent of x more accurately. So we could begin by factoring out 4 tangent of x. Now, if we were to divide 4 tangent squared of x divided by 4 tangent of x, that would leave us with tangent of x. If we did negative 12 tangent of x divided by 4 tangent of x, we would be left with 3. And that would be your answer for example 8. Okay, 9. I am going to rewrite that one a little bit differently. We have cosine and sine here. So how about we do, instead of cosine cubed of x, let's just do x cubed minus 8. Instead of sine cubed of x, let's just do y cubed. And now we have a difference of perfect cubes. 2 sets parentheses. This is that type of problem that requires the acronym SOAP. Okay, now in order to, let me take care of this acronym first. So SOAP is an acronym stands for same, opposite, always positive. So we want this sign in the parentheses to be the same as that one there. So same, opposite, always positive. This value here, we're going to get this value by taking the cube root of x cubed, and that would be x. We now fill in this space here by taking the cube root of this term, which would be 2y. This is part A. This is part B. And here's how we're going to fill in the rest. We're going to take your A term and square it. We're now going to multiply our A and B terms. Then we're going to take our B term and square that. Okay, well, that's what our answer would be if this was this problem. But it's really this problem here. This just kind of helps serve as a roadmap to help us with our answer. So now we need to take this answer here and fill in cosine for x's and sine for y to get a final answer that looks like this. Just realized I wrote a y there when it should have been an x. My bad. I'm sorry. It's the end of the day. It's 4:30. I'm tired. Okay, example 10. This is kind of like that difference of perfect squares problem that we did a little bit earlier. Instead of sine to the 4th power of x, we could do x to the 4th power. Minus, instead of cosine to the 4th power of x, we could do y to the 4th power. Okay, this is a difference of perfect squares. This is the same thing as same thing. Square root of x to the 4th is x squared. Square root of y to the 4th is y squared, but please take note, that one can factor again. So I'm first going to copy down this one again. And then this one we can factor one more time. Difference of perfect squares. The square root of x squared is x. The square root of y squared is y. And now we're just going to fill in sine and cosine accordingly. Forgot my parentheses. And this right here, that'd be your answer for number 10. Okay, 1 minus cosine squared of x, or 1 minus x squared. We have a difference of perfect squares again. The square root of 1 is 1. The square root of x squared is x. Now just replace these with cosine of x. Okay, 12. Another way we could rewrite this. Boy, that looks familiar. Did we do this one already? No number in front of x squared, so we can go ahead and plug them right into parentheses. Hard part's done. $13. Here we go. Let's multiply 12 times -6. Need the factors of -72 that subtract to get -1. And now we can create our grouping problem. And out of that group, looks like we could factor out a 4x, leaving us with 3x plus 2. Out of that group, we could factor out a -3, leaving us at 3x plus 2 again. All right. Here's your final answer. Okay, this one here, 14. Looks like they have a secant of x in common. So let's start by factoring that out. And that would leave us with secant cubed of x minus 1. Now we have a difference of perfect cubes. Same, opposite, always positive. The cube root of secant cube of x in the cube root of 1. We're going to take this term here and square it. We're going to multiply these two together. And then we're going to take that term and square it. And we are now done